Okay, good morning, everyone. I hope you enjoyed our symposium, the previous day of our symposium. I found it very interesting, so many excellent presentations that we could follow. So now there is a second day. Yesterday I explained all, well, while introducing the symposium yesterday, I started with defining all the terms in the title of our calculus project and how they relate to our research. Now today I would like to introduce very shortly some of the research we have performed in the frame of calculus, but that is not presented today or yesterday because, yeah, there is also a lack of time and the persons or the involved researchers could not be present here. And then I will introduce the program, shortly the program of today. So, yeah, you might know that, and this is also a premise we use in calculus. So in humans, language is part of a larger system for acquiring, representing, and communicating about objects and situations in the physical and the social world. And thus, especially this grounding in the physical world, this is what is, for us, what was important in calculus. So the representations that we build, somehow we want them also to integrate this physical knowledge into the representations. And then we want to see how can we then reason with this kind of representations. Now, yeah, this phrase, yesterday, it was very important. We looked at all the models or the models that are inspired by the human brain or maybe other biological brains. And that it seems, well, also in what I'm going to tell very shortly about other research done, it is humans have a mechanism to reason. And we have quite also very recent studies that show that the mechanism to reason in the human brain is different from the mechanism or from the areas in the human brain where the language processing takes place. And that also must put us thinking of, yeah, okay, we have this language processing, we have our large language models, we kind of mimic that process of language and language generation. But once we want to reason with the representations, maybe something else is going on. But of course, this is still a very open area of research, so where I think still a lot is to be done. Now, in calculus, we also postulated that humans are very good in geometric reasoning. So they can really imagine, yesterday also I spoke a lot about imagination, so they can imagine positions, routes, angles, and they can make computations in this 3D dimensional space. So you can imagine distances, routes, and so on. And also you can link this to time, so in a 4D dimensional space. And this is also what we try to do in the work, well, what we accomplished in the work of Guillaume Collel, who is now a researcher at Huawei. So in this paper, we trained from paired language and visual data, so descriptions of an image, and just with a very simple regression model, we predicted the position of object in relationship to a person when that person was performing an action. So if you fly a kite or you hold a kite, that kite is at a different position. And this is also something we need in language understanding, because in a text or when we have a dialogue, we will not explicitly tell you where that kite is or so. But if we talk to a robot, that robot should know, well, should somehow know that information. Now, in this work, we showed that, it's already a while ago that we published this, but we showed that from the word embeddings, we could generalize. So if you see person holding cat there in the middle, so in this case, the cat was not seen in the training data. So we had some paired training data where we had sentences, here represented by these triplets, so where these sentences were paired with images. But so you see here all the underlined words, they were not seen in the training data, but with the word embeddings that we used at that time, we could, somehow similar words could be found, and we could still predict correctly where these objects were positioned with regard to that person. And when we used randomly initialized word embeddings, that was not the case. So we could generalize already from these word embeddings, but yeah, Ruben showed you yesterday another case, what with unexpected situations. So when also where you here we train from these paired images, but humans can very easily imagine also these unexpected situations, like a horse on top of a man, what he showed yesterday. We will also today look at reasoning in the sense of discovering causal structures in data, and in assessing to what extent the discovered structure is accurate. This is the work of Nathan that will be presented. We will not go deeper into the representation of space. This is work that I am kind of involved in. So we are preparing a book with Parisa Korjamshidi, James Pustejovsky, on spatial language understanding, representation, reasoning, and grounding. And I think also there we can still do a lot of quite interesting work because, yeah, also the human brain constructs spatial or cognitive maps. Yeah, we have a kind of way of having that information, that spatial information, stored in our brains, and we can compute distances, spatial relationships, without even having experienced that spatial relationships in reality. And also animal brains, I think this is also a very interesting paper in that respect. So also they have a very clever way of, memorizing somehow information, spatial information, and compress it in their brain in a compact storage representation. And when these animals are dropped at some location, they try to find a point that they are familiar with, and from that they can reconstruct routes. So they have a very good way of representing spatial information. And this is also something, I think it's kind of a topic which in natural language processing has been ignored for quite a while, but yeah, that book is upcoming. I said also yesterday that Tuur Leeuwenberg could not be here because of family reasons. But he did very interesting work in the frame of calculus. So he translated language to a timeline. And he has a paper where we predict from language relative timelines, and also where we predict from language absolute timelines. Of course, you know, language is underspecified, so it is more in the absolute timelines. It's more like the range in time where something could have happened, and the range is represented as a probability distribution over kind of discrete time points. And then this is also very interesting research, which Victor Milewski will dive in today. This is about the structure of language and the structure of the physical world. So we were in calculus very much intrigued by the question, what influences what? Is it that language has a universal structure which corresponds to the physical world? So basically, we humans, we all see a physical world which has certain regularities. And is it the physical world that has influenced our language and our language structures? So like the spatial geometry that we see in the physical world. So it could mean that we could recover language structure based from on the physical reality. Or is it the other way around? Is it language that influences how we see the physical world? So we put our view upon the physical world by using language. Can we predict from language then, somehow the layout or configuration of this physical world? We don't know, but you will see that Victor made, he performed a number of experiments which might reveal a bit in what direction we could be going. But anyway, I think it's an interesting research question to see how these two structures could be combined into better representations that could serve language processing and vision, computer vision. So then the final thing is, how do we evaluate language understanding? And when we designed a calculus project, it was kind of a continuation of a project that we worked on. So I was coordinator of this Future and Emerging Technologies call. So we worked on a project from 2012 to 2016, where we translated language into events happening in a 3D virtual world. So these were 3D graphics that we were generating both from children's stories and from patient guidelines. At that time, we translated language into a knowledge representation, first order logic, and then we translated this to Unity scripts, which were rendered in this graphical engine. Of course, today we have all these diffusion models, but yeah, the idea is somehow the same. And you could, well, in our previous project, we saw this generation of these graphics as a way of how good we are, how good the systems are in understanding language, in understanding a story, for instance. Now we have these diffusion models, DALL-E 3, for instance, where we perform text-to-image generation, and we have even very recent research will generate text to video, like make pixel dance. So you see this is an emerging technology. So we can now directly generate from language to pixels without that intermediate knowledge representation. And this is also what we will look at today. So we will, in the presentation of Maria Truszka, we will look at how we can control the generation by means of human language. So if we say, I want to have a picture of grass and a tree, but maybe we want to specify. Suppose we are building games. We are a human and we have an interface to build games. Now we want that grass to be dead and we want to have a green tree, but you don't want that the environment changes, the background changes. You only want that the information that you specify changes in the image. And this is still a current research question, and I think also our invited speaker of this afternoon, he will be talking about this topic. And we go then, in our demo, we go one step further. We have, Mingxiao Li will present how we translate, it's still a very simple story, how we translate language to video, and how also it is important to specify, to really make explicit in language all the things which were left implicit in language. So that is something that is important for the machine to be able to generate a video. So yeah, let me again introduce our keynote speakers, James Henderson, Rian Maya-Sachan, Maria Toniva, and Yuval Alaliv. So today we will have keynote presentations of Maria Toniva and Yuval Alalouf. Yuval will be online. I said yesterday also he could, last minute his flight was cancelled. So we expected him here, but apparently from Tel Aviv it's not so easy to come these days. But he will present online. From our postdoctoral researchers, you heard already presentations by Florian Mai, by Ying-Yuan Sun, and by Vladimir Arojo. But today, Maria Trushka will give an additional presentation. From the PhD researchers, you have heard Aris, Ruben. Today you will hear Nathan, Corny, and Victor Milewski, and Mingxiao Li will give the final demo at the end of the symposium. We are also very pleased to have some alumni to speak today. Today, Damien Sirio will give a presentation, and also Graham Spinks will give a presentation, and yeah, he's also excused, he's still in Spain, so that will be also an online presentation. Yeah, you are invited to look at our publications. You can follow the program. You have the program online, but there are also paper. There is also a paper flyer available. So enjoy this second day, and I'm looking forward to all the presentations. Thank you.
No, I'm good.
So good morning, everyone. We are going to have Professor Maria Toniva to give us the talk. Maria Toniva is a tenure track faculty at the Max Planck Institute for Southwest Systems, where she leads the BRAIN team. And her research is at the intersection of machine learning, natural language processing, and neuroscience. Let's welcome Dr. Maria.
Hi, everyone. Just a quick moment. Okay. Okay. I see it in the corner here and down.
Oh, there.
Yes. Huh. Oh, good. Okay. Perfect. Yes. Hi, everyone. Hi, thanks a lot for the introduction, and I'm really, really happy to be here. Thanks for having me. Today I'll be telling you about our research on language modeling beyond language modeling, and it sounds pretty meta, but I will explain what I mean in a second. But first I wanted to tell you a little bit about our new group, which is called Bridging AI in Neuroscience. And so we started it about a year ago at the Max Planck Institute for Software Systems in Saarbrücken, Germany.